Okay. Cool. Okay, any other thoughts? Cool. Okay, so today we're going to talk about spherical spacetimes, a little bit about black holes, and basically taking what we've done so far with both the hydrodynamic evolution equations and the spacetime evolution equations and constraints, and reduce them to a fairly simple case of spherical symmetry, which, you know, it's the first thing you do in physics, right? How can I take this problem and make it spherically symmetric? And there's actually a lot of interesting things you can do with that in GR, right? Because all of a sudden you can treat simple black holes. And black holes tend to be pretty simple, actually. They're some of the simplest objects in the universe. And you can deal with non-rotating black holes all of a sudden just in spherical symmetry. And so there's various ways of doing it. Speaking of black holes, this is like black hole week. So yesterday, LIGO detected another binary black hole merger, first one of the 03, the third observing run. So it's becoming routine, boring, snooze fest. Wasn't a neutron star. And then tomorrow morning, there's a press conference, which apparently is a very poorly kept secret, about an announcement from the Event Horizon Telescope, which, how many of you have heard of that? So they're trying to directly image a black hole. Well, technically the shadow cast by a black hole. You know, they're like, stay tuned for a press event, you know. Well, I wonder what they're going to say. So it should be pretty cool. But black holes abound this week, so watch out for that. Okay. Spherical spacetimes. So we're going to take our 3 plus 1, and we're going to reduce it to just 1 plus 1, where everything, whatever you want to consider, depends on just t, time, and radius, r. So reduced just to time and radius dependent. Now, obviously, you can't treat things like rotation with this, but you can treat simple black holes. Short shield black holes, of course, are spherically symmetric. Our general metric that we'll use, and we'll use this as sort of our starting point for constraining once we pick our gauges. The line element, I'm dropping the time dependence here, so I'm calling this dl squared. This is the spatial line element, is equal to a, which is some function that we'll talk about, dr squared plus capital B r squared all times d theta squared plus sine squared theta d phi squared. And so these a and b are functions of time, some function of only time and radius only, right? And they depend on our choices for the gauge conditions and our slicing, right? How do we set up the lapse? How do we set up the shift vector? And that will tell us how B and A behave. So the full 4 metric, in this case, requires that we know alpha, the lapse, as a function of time and radius, and beta, the shift in the r direction, as a function of time and radius. Right? There's only one component of the shift in spherical symmetry. It's just the radial component of the shift. And you can do several different gauge conditions, and you get different requirements for A and B, different expressions for A and B. For instance, one that we'll talk about later is a radial gauge. In this case, you just set B equals to 1. All right? So this coefficient just becomes 1. You just get the usual r squared d omega there. In this case, if you do that, r is then the areal radius, which we talked about in the case of short shield black holes. So in other words, r is really just equal to the short shield radius, which is equal to the area of the black hole A divided by 4 pi square root, which we can also express as the circumference divided by 2 pi. So that's what we mean by areal radius in that case. It's a fairly simple case. Another one, which is pretty common, is an isotropic gauge. This is isotropic because here we set A equals to B. And then R we express as R bar, which is the isotropic radius now. And now once you've set these two things equal to each other, you've got to solve for them based on the other conditions in the problem, right? And then there's another one which you might call something like co-moving gauge. I don't think the book actually calls it that. But we'll call it that. In that case, you set the shift function of radius, oh, no, I did that right, time and radius, such that the fluid is always at rest. Eraser. So that the fluid is at rest. You almost think about that like Lagrangian, right? So I set my shift vector so that the coordinates move with the fluid. And so that relative to my coordinate r and t, the fluid's not moving. All of these have ups and downs, pluses and minuses. And depending on the problem, you would select different choices for this. And then once you've done this, most of these things constrain beta. You have to also consider your slicing condition, which is your choice of alpha, right? So you got to specify the dependence of alpha as a function of time and radius as well. For instance, and we won't go into too much detail, I'll show you an example later. But remember geodesic slicing? Anyone remember what the definition of geodesic slicing is? What's alpha? It's really easy, right? Alpha equals 1. That's great, but it's prone to singularities, right? And so that's problematic from a numerical perspective. Other choices which are common, we'll talk about one of these today, it turns out. Remember, we talked about this a lot, maximal slicing. Does anyone remember what the quick and dirty constraint for maximal slicing is? That's right, Oliver. Yeah. K, the curvature scalar is 0. And then polar slicing. Now, oh, I didn't write this down. But the constraint here, I'll just do this in spherical coordinates because that's what we're doing today. The trace of K is equal to the contraction of the RR components of the extrinsic curvature K. That's polar slicing. I didn't write that down in my notes, but we'll come to that later. These are some other choices. Now the book goes into some nice detail on maximal slicing. Maximal slicing is pretty commonly used in a lot of different numerical simulations. At the end of today, I will show you the evolution equations based on polar slicing, which is pretty convenient for use in numerical simulation, at least in spherical symmetry, and I'll show you why that is. Okay. All right. Black holes. Treating black holes can be tricky numerically because they manifestly require that there is a singularity. And that, the equations let that singularity appear, it's fine. Equations don't care, physics doesn't care. But numerically, the computer might care, right? At the end of the day. And so how you handle that depends very sensitively on your gauge choice. And not all choice of coordinates will allow you to even handle something like the event horizon. For instance, in short shield coordinates, we've talked about this several times. At the short shield radius and short shield coordinates, there is a singularity. but it's a coordinate singularity. It's not a real singularity, and so you change to something like isotropic coordinates, and you can get rid of it. But there's still the real singularity at the center. And then how you deal with that numerically is tricky. So you want a couple of things. In order to study black holes numerically and in spherical symmetry, you want horizon penetrating, meaning that your coordinates can go through the horizon. Schwarzschild doesn't. And you also want something that avoids the singularity, so singularity avoiding. And various choices do not. And so you need to come up with some scheme for that. There's different ways of doing that, which chapter 8 doesn't talk about. Maybe we'll get to them later, but at the rate we're going, I think I'm going to spend most of the time talking about neutron stars, so we probably won't talk about them. But there's things like puncture method and excision methods, where you deal with the singularity in one hacky way or another to get rid of it from the numerical calculation. Okay, so let's start with a few examples of some of the issues that we run into when we're dealing with black hole spacetimes, and how you can choose your coordinates to yield different results for your numerical evolution. So let's start by assuming that we can express alpha and beta analytically. Yeah. All right, so we've got some simple expression like we had over here. Alpha equals 1, cool. Beta equals 0. You know, some analytic expression that I don't have to solve for numerically. That's going to be our starting point. And lead to killing vectors for the lapse and the shift. So a killing lapse and a killing shift, meaning that there's symmetry in those directions, which also means what about the space-time? Space-time is time independent. I'll call it static. Doesn't depend on time, right? If there's symmetry in the lapse direction and the shift direction. Okay, so let's take our initial data as being space-like. And we're going to express that as v, the spatial three velocity equals 0, is being the space-like surface of v equals 0 from u equal, or velocity, u equals, oh, I'm sorry, 0 is less than u is less than infinity on our Kruskal-Jaqueras diagram. Remember this from way back? I'm going to draw it. So this is a plane in which we often think about black hole spacetimes. I'm going to cut my drawing off, but we can do it anyways. And I think I'll actually just draw this in this plane here. So I'm only going to draw the first quadrant of this. So this is V, and this is U in my little diagram. And this is often referred to as the first quadrant, quadrant 1 of the Kruskal-Jaqueras diagram. And in this, right at 1, that's my singularity, always a squiggly line. And this is V equals U, that line there. It's also R equals 2m, Schwarzschild radius, or the radius of a Schwarzschild black hole, like that. This is R equals 0. The spatial coordinate origin, that's where the singularity is. And that's how it moves in this plane. And V is equal to the positive 1 plus U squared along that singularity in this plane, like that. Okay? And then I think maybe that's all I need for the moment. But anything falling in this plane, for instance, we could have something falling, starting out from some location in this diagram here, and it's going to fall in that's a geodesic or a free fall world line. It's going to fall in past the event horizon and into the singularity. So that's our rough diagram in this U and V plane that I'm talking about here. And so we're taking our initial data as being V equals 0, from U equals 0 to U equals infinity, right? Like that. So that's where our initial data are going to lie. Makes sense? Took me a while to draw that. Okay. This is equivalent to, in short shield coordinates, the short shield time equals 0 from 2m less than equal to the short shield radius less than equal to infinity. So outside the event horizon. That's the same thing, right? Taking these initial conditions, V equals 0 from U 0 to infinity, is the same thing as saying my short shield time is 0 and I'm outside the event horizon of the black hole initially, right? So we're gonna see how that evolves, how the space-time outside the horizon evolves from t equals 0 in short shield time. Okay, so now let's make a gauge choice. Let's choose our lapse as a function of the short shield radius to be equal to 1 minus 2m over the short shield radius to the 1/2. And let's choose beta as a function of rs to be equal to 0. Very simple. Plugging that into, and I've already erased the metric, which I should probably write that metric down. I'm just going to write it down because you're going to see it again and again today. So I'm going to write that over here just so that we don't forget it. dl squared is equal to a dr squared plus b and r squared d omega squared. And you know what I mean by this? This is the solid angle. Okay. Right. So this leads, once you select your alpha and beta as analytic, they don't depend on time, right? And so that gives me my static space-time constraint. There's no direct dependence on time in either the lapse or the shift. Okay. So plugging this in to our line element, we get capital A as a function of the short shield radius is 1 over 1 minus 2m over the short shield radius, and B as a function of the short shield is equal to 1. Right? And so that's similar to our radial gauge, right? It basically gives us our radial gauge that we had before. Okay, and it's static. Nothing depends on time here. All right. Let me erase my metric again, because I'll come back to that, right? This is just a general expression for the metric, but I'm going to use those capital A's and B's a couple of times. Okay, so the asymptotic limit is reached. So you can just look at those and see that the asymptotic limit, which in short shield time is when the short shield time is equal to infinity, or as it approaches infinity. And this means that the short shield radius is 2m. So just looking at those coordinates, right? As the time goes to infinity, my radius goes to 2m, and the lapse goes to 0. That's where everything stops. So this means, right, that if I evolve forward in time from these initial conditions with these gauge choices, anything outside the event horizon never crosses the event horizon. So the coordinates don't even cross the event horizon at infinite time. And so this is not horizon penetrating. These gauge conditions cannot penetrate the horizon, okay? Therefore, no time slice, as we march forward in time, penetrates horizon. So we can't learn about anything inside the horizon. Okay? It is singularity avoiding because it doesn't get there. So that's nice. But we can do it, and we did this before when we were talking about short-shield black holes. We dealt with this before, right? There's a singularity at the horizon. And the way we dealt with it was to do a coordinate transformation. Specifically to isotropic coordinates, which we talked about, I think, in even one of the homework problems. You've got to work with isotropic coordinates, r bar. And in this case, if you make that coordinate transformation, the lapse as a function of r bar is now 1 minus m over 2r bar. That's got a, no, that's good, okay. I have those cut off. M over, divided by 1 plus m over 2r bar. Like that. And then the shift, beta r bar of r bar, right? So in the r bar direction is 0. So those are my isotropic coordinates. Now plugging that into here to re-express my A and B, A of r bar is equal to B of r bar, as it must be for isotropic, which is equal to 1 plus m over 2r bar all to the 4th power. This is the same time slicing as the short shield coordinates. We haven't changed the time slicing, only it's the spatial coordinates. But this is still not horizon penetrating. I said we were going to do that. I didn't mean that. This still has a singularity at the horizon, where alpha goes to 0. I think it's just a little more apparent in those coordinates. Okay, but we can still change our coordinates to Kerr shield coordinates where we can penetrate the horizon. And that's a common approach for dealing with black holes in spherical symmetry, is to transform to Kerr shield. Shield coordinates. Okay, so here, my lapse as a function of the short shield radius is going to be equal to rs over rs plus 2m, all of that square root, and beta in the rs direction as a function of rs is going to be equal to 2m over rs plus 2m. So this is, we even did this coordinate transformation before. Did we talk about it in class? Remember, it's been a while. It would have been, it's in the beginning of Baumgarten-Shapiro. So this transformation to Kerr shield to get around the lack of horizon penetration. So this gives us, plugging it in, we're still in short shield. A is equal to 1 plus 2m over rs, and capital B of rs is equal to 1. So radial, it's a radial gauge. There. And this is actually horizon penetrating. There's no problem with going past r equals 2m, right? And so you can see that by just plugging in r equals 2m here and here, and this is not 0, right? The lapse is not going to get to 0 until you get to 0, meaning that the lapse reaches all the way down to the singularity, like that. So that's fine, but this does not avoid the singularity. It penetrates the horizons, but it does go all the way to the singularity, and so you have to worry about that when you do the numerical calculations. This lends itself to things like excision methods and puncture methods, but you do have to worry about that. Okay, in order to set the initial data here, and let's go through an example of this very quickly. And we're going to reuse our diagram there. In fact, I don't really even hardly need to change it. Okay, so in order to set the initial conditions, for instance, in a Kroskal-Jakiras plot, we need to find a time slice to start from, okay? So we must locate a time, and I'm going to call it the KS time, equals a constant surface or slice to determine initial conditions. Meaning that I need to find this time equals a constant slice where I can set all of my metric, all of my curvature coefficients. That's where I need to solve that. And once I do that once, I can then march forward from that time slice, having set my initial parameters, my initial data, solving the evolution equations, solving and obeying the constraint equations as necessary. Okay. So, this is left as a homework problem in the book. I probably will not actually assign it. But you can solve then U and V in this plane in terms of the Kerr-Shield time. And that's going to give you the following. U is equal to 1/2 all times the exponential of TKS plus RS all over 4M plus exponential of TKS minus RS all over 4M. All of that, I'm going to have to erase. All of that times RS over 2M minus 1, close bracket. And then V, very similar, is 1/2 exponential of TKS plus RS all over 4M minus E TKS minus RS all over 4M all times RS over 2M minus 1. Where?
It's not in the denominator.
That's right. That's correct. That's correct. I could write this more cleanly as RS over 2M. Like that. Right? And so these are the same set for flip sign there in the UV plane. Okay? So all of these slices then will penetrate the horizon and reach the singularity. And so let me, yeah. So in this case, oh, I got green. Look at the green. Okay. In this case, the slices of constant time are going to look something like this. They are going to, every time slice, right? Every time slice is going to penetrate the horizon and it's going to reach the singularity. And so, for instance, I might start from a slice that's a little extra curvy. Straight from that initially. There we go. That's prettier. Okay, so I might call this my TKS divided by M equals 0 line. And so that, along this curve in the UV plane, TKS is a constant. That's all that is, okay? And I can use that then to set my initial data and evolve forward in time. In this, well, that was always obvious, right? That this line, I keep doing it. that this line of v equals u is the event horizon, right? That's radius equals 2m. I didn't state that explicitly before, but in a short shield metric, that's the radius of the event horizon. And so this line in this parameter space is the event horizon, right? And so here's where it crosses the horizon, nothing special happens to it, and then asymptotically it gets to 0, where it's at the singularity. And subsequent time slices then look something like this, and so on. And each one of them getting asymptotically closer to, and I'll just write it up here again, T over M. Each one of them getting closer to just being entirely inside the singularity. Like that. And that's just this expression in that plane. Okay? So those are pure shield coordinates.
Entirely inside the event horizon?
No, it wouldn't be entirely inside. That's
entirely inside the singularity.
Yes. It's getting closer and closer.
Okay.
I said that in a very confusing way. It's not inside the singularity.
Yeah.
Okay. Sorry. Yeah, that's right. But spending more and more time, right? More and more of the space, of that space-time is near the singularity, inside the event horizon.
More and more of R.
More and more what?
Of R.
Yes, that's right. That's right. More of the space is inside the event horizon. Right. Okay. Yeah, definitely going to skip the maximal slicing part. You can take a look at my notes for that. But I think the derivation is nice. But what I want to jump to, so there are some more chapters later in the book about dealing with black holes numerically, about excision and puncture methods, what you do once you've selected your gauge and you actually want to simulate a black hole on the domain and have a stable evolution in time. I doubt we will touch on those in lecture, so if you're interested, go take a look. But what I think I'm interested in, I think you all seem to be more interested in matter as well. So what we're going to talk about is stellar collapse in spherical symmetry. We'll use some of this machinery to some extent because we can consider stellar collapse all the way to black hole. All right, so let's talk about stellar collapse. I'm excited. Are you excited? I'm excited. I like it when stars fall down and go boom. Stars. Okay, so stellar collapse is actually historically important to the development of numerical relativity because it was one of the first problems that was actually addressed with numerical relativity in the 60s by May and White. And you go look at their papers in 1966, and they based this on stuff that Misner and Sharp, a formalism developed by Misner and Sharp in 1964. I'm going to write down the Misner and Sharp formulation, which is great for studying everything up to collapse. You can actually evolve all the way to the point of collapse, but once the singularity forms, it crashes, which is not uncommon. But if all you care about is getting to collapse, cool. If you want to know what happens after that, you need to do something. You need to trick it. You need to implement some method of handling the singularity as well as the continual collapse of the star, which there are ways of doing that. But if all you care about is just that initial collapse, you're good. Or if all you care about is collapse to a stable neutron star and not collapse to a black hole, then something like the Misner-Sharp formalism is great. And if you're actually trying to get these things to blow up, generally they don't make black holes when they blow up. It's not always true. So let's talk about Misner-Sharp formalism. All right, so here, this is going to be Lagrangian, meaning that mass is going to be my coordinate, essentially. And it's spherical, spherically symmetric. So ideally suited to non-rotating spherical stars collapsing, okay? If you want to see this in more detail, go check out Misner, Thorne, and Wheeler. It's one of the problems, example 32.7. You'll see that in MTW. All right. Now, write down, if I can turn the page, the diagonal line element in Misner chart as ds squared is equal to minus e to the 2 phi, which is a function of t and a. I will define in a second. dt squared plus e to the lambda, a function of time in a, dA squared, plus capital R squared, which is not the curvature scalar, t, which is a function of t and a, d omega squared. Our solid angle. So that's the metric, the line element of the metric for Misner chart. So let me define some of these new variables that we've introduced here. Okay. R is the circumferential radius, meaning that this is the radius that gives you circumference in this geometry, right? So some circle or sphere centered on the origin with radius r will have a circumference 2 pi. It sounds obvious, but when you're in curved spacetime, it's not always true, which is fun. E to the phi is the lapse. So it's literally just equal to alpha. And phi is the metric potential. And that choice is no accident. It is indeed related to the gravitational potential as you might express it in a Newtonian formalism. In fact, those of you, well, at least Mike, Jen's not here, who've used my code, we basically treat gravity in this way, where we have an approximate expression based on the TOV equations for the total gravitational potential, which includes relativistic effects, energy, and pressure terms, and the more or less the full stress energy tensor, expressed as a gravitational potential. And we have terms in our transport equations, because it's relativistic transport, that go like the lapse. We literally compute this as the lapse, where this is my relativistic effective potential. And so this is a formalism that we actually use. Okay. Now each mass shell is labeled by A. So this is like my mass coordinate. And the world line of a mass shell is R as a function of time and A. So this is a radius, right? This is a mass coordinate, and this is the radius. Now that radius changes as a function of time depending on what mass coordinate we're talking about. Because if we're dealing with collapse, the radius of a given mass shell decreases as it collapses in. Okay? And we can choose, it's not required by this, but we can choose that this approximate Lagrangian coordinate can choose A to actually be equal to the mass, the enclosed mass. If you want to do that, which is common, right? Then it's truly like a Lagrangian formulation. Okay. In this, the 4 velocity is U at A is equal to e to the minus phi 0, 0, 0. Because with respect to these coordinates, it is spatially at rest, right? The coordinates are moving along with the mass shells as they collapse. And so the spatial part of the forward velocity is 0. It's all just moving in this direction. And that is just 1 over the lapse, which we've seen before, if you recall, for 4 velocities of a free fall, right? Okay, so let's define some more variables. Okay. We're going to have the gravitational enclosed mass. You will have seen this expression, or something similar to it at least, when we did the TOV stuff and you're computing gravitational mass. So little m is equal to 4 pi, the integral from 0 to a of the rest mass density times 1 plus the internal energy density r squared times partial with respect to a of r dA. So I'm integrating in my Lagrangian coordinate a. I haven't actually done this. I'm keeping it general. But that's how you would compute the gravitational mass enclosed. Capital U, I'm going to define as e to the minus phi, partial with respect to time of r. And this is a coordinate velocity. So a velocity with respect to those coordinates, this can actually exceed 1. It is not a true 4 velocity. It is a coordinate velocity. And then the radial metric function, we'll call it, is the following. I'm going to call that gamma, and it's going to be equal to e to the minus lambda over 2 times the partial derivative with respect to a of r. So that's my radial metric function. Question?
For velocity.
Yeah.
Not oh, no.
It's normalized, right?
Yeah, that's good.
Yeah. Yeah.
I remember that.
Yep. Thank you, though. Oh, it's good.
Or wait. Sure.
Do you buy it?
Because he is in that range.
Yeah. Okay. Okay. So then, with these definitions, the Einstein field equations become just okay, so I'm going to take these variables that I've defined here, and I'm just going to substitute them into the field equations. I'm not going to worry about this yet. And they become partial with respect to t of capital U is equal to e to the minus phi of 4 pi gamma r squared all over h, the enthalpy, partial with respect to a of the pressure, plus m plus 4 pi r cubed times p, the pressure, all over r squared. Partial with respect to time of the mass, the enclosed gravitational mass, is equal to minus e to the phi, there's more room there, times 4 pi r squared pressure u, pu. And then partial with respect to the mass coordinate, the Lagrangian coordinate of the metric potential is equal to minus 1 over the rest mass density times the enthalpy times the partial derivative with respect to the Lagrangian coordinate of the pressure. And here, my metric function then is 1 plus u squared minus 2m over r, all to the 1/2. And my rest mass density can be expressed then as the metric function gamma divided by 4 pi r squared dA partial with respect to A of r.
To find H.
All right. H is equal to rho naught 1 plus epsilon. Oh, shoot. Right. No, I got that in the wrong place. 1 plus epsilon p over rho naught. Sorry. Think for a second. That's the enthalpy. Okay. All right. Now, start making some simplifications. We're going to assume that the pressure is a perfect gas and that the stress energy tensor is that of a perfect gas. Now, if we differentiate this equation with respect to A, what I get is the following. Partial of A with respect to M is equal to 1 plus epsilon gamma. Right? Just substituting this expression in, right? So I did away with the integral, substituted this expression in to there. This canceled, and I end up with this simpler expression. See that? I'm going to use this. I'm going to get rid of the integral because I'm taking the partial derivative of m. Substitute that expression into there. I just end up with that. All those terms cancel with the rho naught and the r squared and the partial a r. Okay, so that's that. And now we can use my definition for the rest mass here in the equation that I've got. Which one? No, I think I've erased it. Oh yeah, I erased it. So I want to solve for the e to the lambda, and equation that has been erased. But what I end up with is e to the minus lambda over 2 is then equal to 4 pi r naught, I'm sorry, rho naught r squared. So that tells me a constraint for lambda, how to solve for lambda. And then finally, to finish this system off, I need an EOS. And I also need the first law of thermodynamics. And so I need to know how the internal energy evolves with time, because that appears in my equations in several places, right? And so just from the first law of thermodynamics, we know that this is equal to minus p partial with respect to time of 1 over rho naught, the specific volume, right? And then P has got to be equal to some function of rho naught and the energy. And that's our EOS. That's the first law. The simplest thing to do, of course, which we will do in this case, is assume a gamma law, that P is equal to gamma, some adiabatic index, minus 1 times rho naught epsilon. And then the last step is to just specify boundary conditions. All right. And they're actually, you could probably guess them. All right, I'm going to do it this way. I'm going to make you tell me. So at A equals 0. So that's the origin. So at my coordinate origin in Lagrangian coordinates, what's R?
0.
There we go. What's U? Oh, I wrote it down. It's 0. All right, what's gamma? What's the metric function?
We'll have a zero as well. Yeah, low.
Will it though?
Because M should be zero. Oh, yeah.
It's a race. It's a race. So which is going to go to zero faster? Yeah. And so then what's gamma?
1.
And you've already said this. Good. Okay. Now, at A equals A total. So the outer limits, right? Could be the edge of the star, let's say. Pressure equals what?
0.
So this is bringing back memories of your TOV, right? E to the phi is equal to what? Oliver should tell me this, because you asked about the normalization of the 4 velocity. So at this outer limit, what's E to the phi got to be equal to? If we want to keep that 4 velocity normal. Okay, that's it, right? That's our conditions there. The attraction of this scheme is that written down in this way, it's actually very similar to Newtonian Lagrangian hydrodynamics, which is why this is where they started, because they had plenty of Newtonian Lagrangian codes that they were working on at the national labs at that time at Los Alamos. And so adapting this for GR, it was the most straightforward way to go, because this turns out to be fairly similar to Newtonian. It works fine until you get a singularity, then it crashes. Now, extending this to multi-D is very hard, and that's true for most Lagrangian codes. This is what we would call a grid-based Lagrangian code, right? It's not a particle-based Lagrangian code. I haven't talked at all about particle-based codes because I don't believe in them.
3 months.
Sorry, Steve, that's what you're working on this summer, right?
Only for 3 months.
Only for 3 weeks. We'll let you back. The reason being, in Lagrangian grid-based codes, hey, my hat's gonna work. Okay, so I've got some fluid element, right? This is my fluid element. And I can shift and shape this thing, and its mass doesn't change, right? But its spatial shape does, its volume does, everything about it does. What can happen in a grid-based multi-D Lagrangian code is that you can get shear of a mass element to go like that. When that happens, the code crashes. This is called a bow tie effect. See? And it's very common in multidimensional applications, and whenever you have instabilities, right? Because those mass elements are trying to curve around and grow into an instability, and the code goes. So generally these days, we tend to use, especially in multi-D, Eulerian codes, but there's other approaches. I'm not saying it's the only way to go. So let me now finish by very quickly, and I do have time to do this, write down 1D spherical Eulerian GR hydro. And so this is a common application. And it ends up being almost as simple as this case. I think even maybe a little simpler. So I think I just got a paper cut. Eulerian 1D GR hydro. So now we're not going to fix this Lagrangian sort of coordinate. This is based on my collaborator's code, Evan O'Connor, and the reference is O'Connor Knott 2010. Here we're going to use the radial gauge polar slicing. So we've talked about both of those things. B equals 1, and then this is a constraint on the trace of the extrinsic curvature, okay? Here, in this, the shift vector vanishes, so beta equals 0, convenient. All right, and the metric is diagonal, which is also convenient. We don't like to have to deal with off-diagonal components. And the metric is also extremely similar, though not exactly, a short shield metric. So it's very, very similar to short shield metric, but it admits mass, right? Short shield metric is for a vacuum. The metric here admits mass. All right, and so the line element, ds squared, is equal to minus alpha as a function of radius and time, squared, dt squared, plus a capital X as a function of space and time, squared, dr squared, plus r squared, d omega squared. And you'll note, by comparison to my general line element over there, b is equal to 1, as it must for a radial gauge. Right? And we'll use the polar slicing constraint in a second. And so now I have these functions. That's my lapse, obviously. And then this is a spatial function x, which depends on space and time as well. So I need to solve for that. Okay. Right? Do I have room to write these down? I think I do. Okay. So now our choice, our gauge choice for alpha, I'm going to leave off the dependency in the, for the sake of space. Very similar to the choice that I made for alpha before, off by factor of 2, right? Where it's the exponential, well, this is exactly what I had before for the Misner chart. This is exactly what I had before, right? The lapse is equal to the exponential of the metric potential. And then this x, I'm going to leave that off just for space, is equal to 1 minus 2m as a function of r and t all over r to the 1/2, where this n is my enclosed gravitational mass, right? Like what we had before. It's the exact expression that I erased. That was over here. Okay. So those are that's my gauge choice. That's what I'm going to do. That's my metric. And then I can solve for the space-time and the hydrodynamics bound up together doing this. Okay? Actually, it becomes pretty simple once you write it all down. Okay, let's do that. Here, for matter, we're going to do the usual thing, right? We're going to say that I'm going to use T mu nu. I'm going to use Greek indices because that's what the paper does, and I don't want to have to screw up and get the wrong things in the wrong place. So we're going to take our usual perfect gas stress energy tensor, rho naught h u mu u nu, plus pressure times g mu nu. So that's my stress energy tensor. And then the current, my mass current, J mu, is equal to rho naught U mu. That's our mass current. Okay? And then, once again, the enthalpy is 1 plus epsilon pressure over rho naught. That's the enthalpy. And here, my 4 velocity U mu is equal to W over alpha, W VR, 0, 0. That's my 4 velocity. And W, of course, is the Lorentz factor, which is 1 minus V squared to the minus 1/2. It's Lorentz factor, as usual. Okay? And this V, if I'm just writing down V with no components, is X times VR. Okay? I can write here. Okay. Using the Hamiltonian constraint, we can derive an equation for the gravitational mass with all of these conditions that we've met here. I haven't actually specified the gravitational mass as what I had before. Hamiltonian, I'm just going to write this, leads to mass as a function of space and time is equal to 4 pi 0 to r rho naught h w squared minus p. I'm going to leave that off for the moment. R prime squared dr prime. So that's just from the Hamiltonian constraint. The other mass equation that we had in Lagrangian came from the Hamiltonian constraint as well. I just didn't explicitly state that. Okay. And then the momentum constraint plus polar slicing. So now polar slicing, just recall, the trace of K is equal to what's that called? The inner product. No, contraction. Ugh. The contraction of K, RR. It's getting close to the hour. My mind goes numb. Okay, that gives me the metric potential, which is equal to
Yeah, that's a contraction with R as an index, or just the R component?
R component.
So it's, okay, so now you can contraction. It's just,
Yeah.
okay. That's just wondering why you call it a contraction.
It's not, yeah, those aren't even components. Yeah. That's just KRR. Well, what would you call it? My mind's numb. X squared mass R prime T all over R prime squared plus 4 pi R prime all times rho naught H W squared V squared plus P, the pressure, leave that off, dr prime plus some constant, some initial potential. And that initial potential we solve by essentially applying a boundary condition, which is that at the edge of the star or wherever, the metric must agree with the Schwarzschild.
So why didn't we do this in the previous?
Why didn't we do this what?
In the previous?
I didn't bother with all this extra steps.
Because then we just have zero.
That's right. But here we have, because it's Eulerian rather than Lagrangian, and everything's in R instead of some Lagrangian thing, we need to go all the way out to vacuum and match to Schwarzschild, and what Schwarzschild would give us in an Eulerian formulation. Yeah. Okay. So once we do that, we just get at R equals R star, let's call it the edge of the star, phi R star and time is equal to natural log of the lapse at R star and some time t, which of course it must be, right? That's our definition for the metric function, metric potential. And then applying the Schwarzschild metric to this, we find 2m of R star and t all over R star. Like that. Okay. And then the matter evolution, once you've done this, you just plug this into the old hydrodynamic equations that we had, like for the Wilson scheme, or what we talked about from Mosta et al. When we talked about MHD, said all B equals 0. And you can write this out in a way that explicitly has the geometric source terms. I don't have time for that today, but it's in my notes. And so if you care about the set-off problem, for instance, the geometric source terms are written out explicitly here. or an Eulerian formulation. But this then becomes pretty simple. And so the space-time evolution is essentially coming from integrating this metric potential at each step, right? It's pretty analogous to Newtonian dynamics at that point in 1D spherical, where you would integrate the mass as a function of radius to get your gravitational potential, right? Very analogous. But now this is a somewhat more detailed expression, right? And you've got this condition coming from the short shield metric on the outside that sets the normalization. But this formulation is very, very, very similar numerically to a Newtonian scheme, which is why it's pretty nice in spherical symmetry. This is actually equivalent to a conformally flat scheme. Remember we talked about those? This is equivalent to a conformal flatness scheme, which in spherical symmetry is not approximate. So in spherical symmetry, it's exact, right? We talked about conformal flatness being an approximation, but it's not in spherical symmetry. Yeah, that's all I got. Questions?
In 1D codes, does that d omega squared term in the metric, does that go to 0 or 4 pi? Or does
4 pi. Yeah.
So we don't get rid of it, it just we pretend it's constant.
Yeah, we pretend it's constant. Yeah. You don't have to solve for it explicitly, nothing depends on it.
And also in that case, for some of the things like we need the determinant of the metric, would you just take theta equals the pi over 2 or something then?
Sure. Yeah.
Because that would change. I mean, if you set it to 0, the determinant will go to 0.
That's right, and you don't want that.
Yeah.
You don't want that, right? Yeah.
So in this case, it's just assuming you're just on one polar angle. And
that's right. And if anything in your calculation depends on that, which it might, because you can actually include rotation approximately in 1D. And in those cases, then you do assume that it's equatorial. And so you do pick a theta in that sense. But the determinant of the metric does not appear explicitly anywhere in these equations. You don't have to deal with that explicitly.
Yeah, no, it appears in
the other formulation.
On the redefinition of the conserved variables, there's factors of the determinant there for the hydro.
Yes, depending on how you choose to do it, which the way I wrote it down here, we do not. We include the lapse and the x function. Yeah, which I didn't write down the conserved variables because I didn't have time, but they're in my notes. Cool.
And the only thing then we're really evolving is just the hydro equations, and then after doing that, solving for the lapse, or not that, or
the metric potential.
So
Yeah.
there's no evolution equation for that.
This is the evolution equation.
I mean, it's not. We don't have some other
Nope.
system of PDs.
That's right. It's real nice. It's real simple. This is what GR1D does. This is GR1D's metric and evolution equations.
Never actually the metric that I was on some of the transport stuff.
Here it is. All right. Thanks, everyone.
Everything I wrote for metric code is way over. I will make that simple. As far as any of the parts you don't need, just have something that takes a metric from your function and engineer it with whatever it needs.
And then just sort of adjust them to whatever